Good morning and welcome to today's webinar on 3DXpert Build Simulation, how to predict failures and optimize your design before printing, sponsored by 3D Systems. I'm your host and moderator, Dan Branch, a tech support manager at 3D Systems. During this webinar, we're going to look at some of the special features of 3DXpert and see how it can reduce the number of tryouts, how it can validate the design of the support structures, as well as minimize build failures, which will definitely cut your production costs and time, as well as prevent potential printer damage. Our presenter for this session is Rocky Borgstrom, Applications Engineer for the 3D Systems Metals Customer Innovation Center in Denver, Colorado. This webinar is being recorded, and we will make it available for viewing after the conclusions. As an attendee, you will receive an email containing a link to the recording. We do invite you to ask questions throughout the webinar. Simply type your question in the question panel at the right side of the screen. Questions will be answered at the end of the session, and if we do not have time to get to your question, we will follow up with you directly after the webinar. So at this time, I will turn the floor over to Rocky.
Hello everyone, my name is Rocky Borgstrom, and like Dan mentioned, I'm an application engineer, so I use 3DXpert every day for my own parts, and I also help customers achieve their products. So quick look at just what 3DXpert is overall. It's an all-in-one software solution for metal additive manufacturing. So it's a hybrid CAD design where you can use meshes, solid models, import your data. It's all in one software package. You can do all of your supporting. You can do build simulation that we're going to talk about today, control all of your print strategies and welding strategies. And this has an integrated slicer and also some post-processing operations. If you want to export to maybe some G code for some CNC machining afterwards. So 3DXpert is not necessarily tied to 3D Systems machines. It'll output files for most other metal printers out there on the market. But it does have some added benefit when using a 3D Systems machine. All of our metal printers will use this software, and we really have deeper control of some of our weld strategies and a little bit more closely knit to some of these machines. Just take a quick look at the additive manufacturing workflow. So there's a lot of steps between taking apart design and getting a finished part. Typically that can be in a handful of different software solutions. Maybe you're designing in one CAD package and exporting to an STL file. We all know that that's a one-way street for the most part. It's pretty hard to go back and make edits to your CAD data. In 3DXpert, you can do all of these things in the same environment. So you can jump back and forth. You can jump back into your workflow at any one of these points. I think you can see today we're going to talk about simulation, and that falls somewhere in the middle in general for your part prep. But let's take a quick look at why you may want to simulate some of your additive parts. Metal 3D printing is pretty challenging. It's a lot more going on than a lot of the other additive styles. There's a lot more temperature involved. Anybody that's ever welded knows that you have a lot of residual stress, and you can get a lot of deformation, and we're dealing with those same things here. So because of that, it can require a lot of costly and time-consuming iterations. You know, say you turn over your machine 1 or 2 days, so you're starting a build every 1 or 2 days. You know, if you have 4 or 5 iterations, it can take you well over a week, and that's if you have a very dedicated development machine. If you have custom parts that are kind of short lead time and maybe a little different than the ones that came before it, so custom medical implants, you know, we're just talking things that aren't serial production. You know, you have to do those supporting and pre-processing activities every time, and it can be really time-consuming, and it can cause you a lot of problems if the build fails. A lot of time we want to use it for prototyping parts, mainly machine parts, and those have a lot of undesirable characteristics for additive manufacturing. So we might be able to see what we can feasibly do for a prototype and if that's going to be a good enough analog for what you're looking for. And also post-processing, it can be really challenging to fixture up a lot of parts because we aren't really sure exactly what the finished part's going to look like, maybe until it comes off. You might need to do some 3D scanning to figure out you know, what kind of surfaces you want to use as datums and things like that. So there's a lot of reasons we might want to simulate. And a lot of them come from what can go wrong during a build. So a lot of the main factors, there's a lot more and they're really interconnected, but just a quick overview, deformation in your part. So this is due to residual stress buildup. Can be due to not enough supports, but it can also be due to too many supports or supports in the incorrect area. Maybe you're lopsided a little bit. And definitely wrong printing orientation. That can have a huge effect on the outcome of your part. Coater interference. So this is your coater that's going to distribute the powder across your bed. If you have some parts that are swelling up or deforming and interfering with that recoating system, that can really give you some cascading failures and maybe even crash your build. Material failure is one that's a little more unique to direct metal printing too. You're welding all these parts, so you're building up huge amounts of stress. I don't know how familiar everybody is with thermal contraction, but it's an incredibly powerful force. It can really deform your parts in ways that may seem maybe unrealistic at first, and excessive post-processing. So maybe if you just have too many supports or supports in bad areas, they can be impossible to remove or just very time-consuming. And we definitely want to avoid that if we can. So how does build simulation in 3DXpert solve some of these problems? Well, build simulation is it's an FEA simulation, so it's pretty accepted across the industry, but it's mostly in design and analysis. It's a little harder to use for situations like this where maybe the process is very, very complicated. You have a lot of things going on. The computational time for that can be really huge to do a full simulation. So what makes build simulation in 3DXpert a little different is that it's focused just on this build environment. So it's going to do the simulation of the top layer, and it's going to flow that simulation results down through the rest of the layers below it to really kind of show how that stress state evolves over time. And it's real-time feedback too, so you can see, you can watch as each layer is calculated. Maybe you find an error down early, and you can fix that, restart your simulation, and go back through. The thermal factors aren't really as important in this, believe it or not. We do a physical calibration sample, so you can see down on the bottom that bending is what would be measured. So you would print that on your machine with your powder, and it's going to be a physical calibration for that entire system. So even though material properties should be very similar if we just know what your material is, we get a little bit better fidelity and a little bit more robustness of the simulation when it's matched to your specific parameters. And this also can be offloaded to a computational machine, so you're not tied down to locking up an entire workstation for a whole day as this build simulation is running. You can continue doing other work, preparing other parts, and just check back on that simulation periodically. So we're going to take a quick look at kind of what we're going to see as we jump in the software here, just so we kind of all know our way around. So the first thing is materials. So I touched on that briefly in the last slide, where you do run a physical calibration. We have some validated 3D systems materials in 3DXpert, so those are powders that we sell for use in our machines, and we have those materials preloaded. The element size and layer height is basically defining how many elements you have. So FEA stands for finite element analysis. So basically you're breaking up your part into a bunch of small little beams that you can do simple equations on, and there's just a lot of them. So that's really what drives the computational cost of a simulation, is the number of elements. So you could have a really large model but have large elements, and it might not be computationally intensive, but you might have a large model and maybe a small feature that you want to try to simulate. If you really shorten up your element size and your layer height, your number of elements can grow exponentially, and your computational time can as well. So you really want to remember that this is a simulation. You don't just have to drop your part in there and simulate the whole thing or simulate it on any given resolution. We just want to make sure that the resolution is good enough to get valid results. And when you start a simulation, you can also choose to calculate some other models. So you have some heat treatment models that are going to look at some of your residual stresses and relaxation. And then you have a compensated model that is going to give you an idea of what kind of pre-deformation you could do to the part to produce a near net shape with that given support structure. So some of the results that we're going to see, we're going to talk about displacement, and that's just total deformation of your part, X, Y, and Z. We have recoder interference, and that's deformation in just the Z. So that would be kind of how your part's going to swell up out of the powder bed. We have displacement in the X and Y. So that's removing that Z component, and displacement in X and Y is pretty useful in certain situations. We'll look at stress, and that's going to be the total stress. And that's, we aren't trying to predict the final stress state of your part for you know, any future loading or things like that. We're mostly using it as a tool to look at and understand how the stresses are evolving as your build progresses. And plasticity, lastly, is it'll just highlight the areas where stresses are above your yield stress. So you can't really, doesn't really gain you a lot to continually artificially raise those stress levels, so we transferred over to plasticity, and that's just a measure of damage. And then model views. So we'll be able to see the original model. We'll be able to see the preliminary mesh, so that's before any of the calculations are done to it. We have some analysis models of the part and supports, so you can separate those and focus on just your supports if you see some issues there, or obviously just take a look at your part and remove your supports so you can see a little bit better. And then we have the calculated models. There's an array of them. Those may be pretty situational and not necessarily applicable to all situations. And then lastly, at the bottom, we can display mesh facets, and that might just make it a little bit easier to kind of see what's going on as we're doing this. So we're going to jump into a quick video of starting a simulation and just try to get a feel for what the software looks like and the environment that we're going to be working in. So this is the 3D printing environment. So you can see we have all of our CAD tools on the top. We have all of our 3D printing tools on the side for part preparation. And then, of course, our part in the middle. And I just have a simple frame here. You can see I added some simple supports. They're very thin walled. They aren't very dense. So we're just going to go over and select Build Simulation. And we have those first initial windows that came up. You can see element size, layer height, and our other calculated models. We're going to go ahead and leave those on, heat treatment after printing, which would be typical. And we're also going to do a calculated compensated model after printing. You can see we're using titanium, and that's a validated 3D Systems material. So once we hit start, you can see that it'll create our preliminary mesh, and that's what it did just there. We can spin the model and look around, hide our original model. And we'll start to see in the bottom that little bar start to tick up. And it's already calculated 4 layers of 51. And you can see that we can kind of cruise through those as they become available. We'll skip forward a little bit here until the simulation is finished. And we're just going to go ahead and scroll up. So we're looking at stress right now. So you can see how it kind of evolves as we get new features involved. So the first thing that we saw, or the first result, I guess, is displacement. So that's typically one that we want to look at pretty much every time. And that's the main geometric concern for most people is, the final dimensions of your part, whether those are going to be in tolerance, and a lot of additive we're seeing, I guess, in all of engineering, we're starting to see a lot more GD&T and surface tolerances, certainly for topologically optimized parts and more organic parts. It's hard to just do a basic measurement with calipers. So we really kind of want to understand how those unique shapes are deforming during our build and what we're going to get out. And they're certainly not always intuitive. This part that we're looking at today will be intuitive for the most part, but there's definitely some nuances to it that are a little, I don't know, they typically get overlooked. And we definitely want to make some intelligent trade-offs based on some of this information. So, we might have some areas with some deformation. We might be able to add some more supports, but we really may not want to, and we may be able to absorb a little bit of deformation with just a little bit of stock to be machined off later. Recoder interference. So you can see in the top right, that's a part that picked up out of the plate. And you can see the result of the simulation in the bottom right. So those units are in millimeters, so that part is just deflecting up 8 microns, and that might not seem like a whole lot, but it's enough to reduce the amount of powder above it. So you can get some different welding characteristics. And we'll see later on that there's some other things that come into play with some part failures of this type. And these are kind of dangerous too because you have some part deformation, but it can also crash your build. So you might not just lose that one part, but you might lose every other part on your build plate. So this XY displacement, that's the Z component removed. This is really useful to see shrinkage lines. So this is something that really catches a lot of people's eye when they start looking at metal additive. you'll see them pretty much anytime two features come and meet kind of up high in your part. So as that top beam is welded across the top, that thermal contraction is going to pull those two vertical columns inwards quite a bit. Part stress. So this is residual stress buildup. Red is more stress, and gray is very minimal stress. You know, this part where we do have a lot of features coming together up high, we are going to get a lot of stresses. If this part was inverted, we would see a lot less stress. So you can use this to look at different orientations and see if it's possible to build your part without doing an initial stress relief before you remove a lot of your supports or you remove it from the plate. We usually always recommend to do some sort of heat treatment, but if you can get away with not doing a stress relief first and do a lot of your post-processing machining and then do a hardening step at the end, you can really cut down on a lot of lead time and a lot of cost in post-processing. Plasticity, so this is damage to your part. So strain is defined by the change in length over the original length. So usually the value is really small. 2% strain is usually the edge of your elastic strain that's recoverable, and then where you start to get into plastic deformation. And that's what we're looking at here. So once your strain gets over the yield strain of your part, every material is going to have a yield strain, just like I'll have a yield stress. That's the value of plasticity that we're going to see. So any positive value of plasticity is going to be potential damage to your part. And when I say potential damage, it should be noted that all of these parts will basically always have some form of plastic damage, and it's usually unnoticeable if it's just surface damage and a little bit of curling, but it's still damaged, but it's absorbed during the printing process. So it can be absorbed in that layer height and remelted, but it's still there. Don't want to ignore it. So just a quick summary, recap before we jump back into another video and take a look at some of the iterative processes here. We're going to look at deformation, especially shrinkage lines for these particular parts. We're going to look at coater damage, and not just in the caused by that Z deflection in your part. We're also going to look at cracking and plasticity issues as well. So we'll start this second video here. So we're looking at that same part. You can jump back into that build simulation just by entering the Build Sim tab. You don't have to redo the simulation. We're going to show our analysis model and hide our original. And we're just going to scroll up. We're looking at XY displacement here. And everything looks pretty good. You can see we're starting to see some red, and our displacement value, our max up here, just jumped to 440 microns. But that was in the support. So if we hide the support, you can see it drops back down to 50 microns. That's about half a weld path. So really aren't seeing too much until we get to that connection. And you can see it jumps right back up to 450 microns. So that's a pretty significant deformation. But let's look at what that looks like on a part. So here it's immediately obvious that you have a line here. A lot of people think it's a positive sometimes, but it's really that negative is your deformation. You can also see on the top left you have some curling. I don't know if you noticed that in the last image, but it's there. And here's a 3D scan I did of that part. And you can see very well correlated with that single point deflection. So to reduce that, we're going to want to kind of reduce the amount of material we have in that top connection area. So I tilted this part back to about 45 degrees. I have just some thin supports there just to try to hold it up, not really try to restrain any of the stresses. So we'll hide the views again, and we'll look at X, Y, Z displacement here first. So you can see we kind of have some hot spots down on these edges. Some of that is that Z curl up, so we'll look at X, Y to kind of get rid of that and just focus back on our shrink lines. You can see similarly, everything's pretty good until we make that connection, and it jumps quite quickly up to 200, 300, 400 microns. So we did better, but we're still seeing a lot of deflection. And this is kind of one of the unique unintuitive things there, is that that top red section in the top left is actually coming after we connect, and it's because of that angle and dissimilar cross-section where that material on top is pulling it inwards. So you can see our part, we have that distinct shrink line where they come together. And at about 200 microns, 300 microns, you would still expect to be able to see that with your eye. So we're going to try to reduce that amount of material a little bit more. So we're going to tilt this up on another axis, jump back into our sim. And these are all the same part that I went back into and re-supported. These aren't different models. I just went back and reoriented this and ran the simulation again. So we have even worse deflection on that edge. That was up to 500 microns. And you can see we have pretty bad Z deflection for coder damage, up to at least 10 microns just in deflection. Let's look at our area of particular interest here. And it's what we would expect. Roughly 100 microns deflection as we connect. That's quite a bit better than we saw before. 3 or 4 times better at least. And this is typically what you end up doing with a lot of, or trying to do with a lot of 3D printed parts. You can see there's no visual coder or shrinkage lines there, but we do have some problems on those down-facing edges. So you can tell at the bottom it started out kind of okay, but we have this cascading failure as we started to accumulate some damage in our build. So we'll go ahead and we'll solve that. We'll add some thin supports onto the bottom, as you can see I did here. So these are thin supports. They're not trying to restrain any of that stress that's accumulating. We're just trying to hold that edge up and get good build quality. Jump back into our simulation, and we'll start out on plasticity because we found that that was probably our highest factor. So you can see we do have a little bit of a hot spot down where the support's connecting the part, but our part looks pretty good in that area where we aren't seeing much deformation. Strain, stress is pretty manageable. See on the edge of that support, we're getting some hot spots. That may be an issue or it may not. Our plastic strain values are still in the kind of on the edge of the acceptable range, usually between 0.01 and 0.02 is where you start to see some material failures, at least for tie. And you can see we had just that. So we had some cracking along our support. You can see it caused our part to shift. So the other side didn't quite tear off like that, but you can see major dark shift lines in our parts. And that's kind of what we'd expect from what we saw in the simulation. Once that part cracked, kind of all bets are off at that point. We're no longer simulating the correct scenario. But, so I'm going to go back and I'm going to add solid supports with a solid connection. These are, I think, maybe 400 microns in width, so not very thick still, but just a little bit better connection. And let's take a look at the plasticity. So you can see our plasticity levels are quite low. We're still at 0.01. And we don't really have any hot spots in that support part interface. We have a little bit on the edge, but our levels are still pretty low. Definitely about half of what we were seeing last time. And we're just going to assume that all of our deformation up top is similar. Back looks good too. Check our coder damage here to see if we do have any Z displacement. Doesn't really look like we do, maybe just a little bit on the edge, but only 2 microns, so not really an issue. And here you can see that part. It's a beautiful part, no cracking, no layer shifts. You can see on the back, there's no visible coder lines. Everything looks great, unlike the one in the background. So I would consider that a good part. It's really not a part that's optimized for additive, but we run into those issues all the time, and we can make it work. But say we didn't want to support all that and we wanted to redesign it, we could add some fillets to the back here. These are just 1 millimeter radius fillets, and I just added them in this environment with some of those direct modeling tools. Undid it because I don't actually want that top to be radiused. But let's take a look at plasticity here. And let's remember some of those plasticity levels that we were seeing before. You know, here it's unsupported. Our plasticity levels are higher than we saw with our supported part, so we can expect some surface damage there. And our displacement is pretty in line with what we saw. It's going to be a little bit higher than the ones where we had some support, because that's going to add a little structure, but we do see that unintuitive hot spot on that left side. So that part was right on the edge. We had some plasticity issues. And this is really an interesting case because we have one half of it that built great, and we have one half of it that kind of had some build issues. So this is actually where we're right on the edge of whether we think it's going to fail or not. And it actually comes down to the ability of the machine and process to compensate and just the robustness of this printing process to account for some of those. So the ones that are undercut were perpendicular to the coder direction, so they're parallel to the blade, and that did some odd things with sweeping powder onto it, sweeping powder off of it, and not a desired way, where you can see if it's at a little bit more of an angle. We do have some kind of rough surfaces on the bottom, but we might be able to machine those away, and we gain a lot of time not having to build all those supports. We're going to jump back to our presentation. I guess just a quick word on this. So that was a pretty general iterative process. It's what seems like a simple part, but it can be problematic to print. Of course, we could just lay it down and have it build like lay it down flat on the plate. We would have a lot less issues, but then we might be a lot harder to remove the part. So if I had a more complex part, that's pretty much the exact process that I would go through. And if we had to build these 6 parts and say we didn't know how they were going to turn out beforehand, that might be 6 builds, 6 development builds, 6 days. That's a lot of time to invest in learning just learning how your part is going to react during the printing process. We really want to shorten that time and not waste time, especially machine time where we don't need to. just look at a compensated model, one of a little bit more complicated part, a little bit more interesting to look at. So this is a satellite bracket. There's a couple handfuls of these orbiting the Earth right now. But it's kind of an interesting part to look at. So the compensated model is that kind of blue teal color. You can see on the top left how it is pushed more to the left of the part. So with that part geometry, the way it curves back in and all of the supports coming down underneath it, all kind of wants to pull those arms inwards towards the center. So you can see the compensated model essentially pushing outwards. So if we wanted to use that for inspiration to change our support structure, we could add supports that are angling away from the part in that direction to try to resist some of that strain that the simulation is going to show. It's possible to print these. You can export them back into your build environment, but generally not recommended for file retention reasons, and the supports don't automatically adjust to the new part, so you would have to re-support it. But it's typically used just to show what kind of issues you might have, because you're probably going to have to go back and have some file retention and at least smooth out some parts of that model just to make sure you don't have any undercuts. Can be pretty important in a topologically optimized piece such as this. So really the main focus of this is that build simulation is a tool. It's another tool in our toolbox. It's an incredibly powerful tool, but isn't one that you can use necessarily without understanding. So the more understanding we have of this simulation, the deeper we can read into what the results mean, and the quicker we can understand exactly what our parts are going to do. Can really gain a lot of confidence too just by using it. It really can help you visualize and see some build issues that can be pretty hard to I guess determine the root cause after the build's crashed. Maybe the contributing factor happened, 10, 20 millimeters below where the build actually stopped. It can be really hard to pinpoint exactly what the cause was. And just a few other examples of maybe some more complex parts, some better uses than that little frame that we had. So custom medical implants, I touched on these a little bit earlier, but these are short lead time parts. A lot of times they can be patient matched. So you already have surgeries planned, maybe the person is in critical condition. You only have, a couple weeks or down to just a few days to make some of these parts. Can't forget that there's a lot of post-processing that needs to be done, and you can see the amount of column supports that are on some of these parts. So this is a hip. The cup is on this left portion, kind of this darker red portion. But you can see this is a displacement, so you're going to have some closing off of that, so that might be a problem if you're going to do some post-machining into that joint. Add some, plastic bearings and such in there. And while the deformation may still look good, you see that on the bottom we do have some plastic deformation in some of these supports. So these supports are probably going to crack. Maybe it happens after the part's been building for quite some time. But you'll still see a layer shift when those parts crack because a lot of that stress is going to be released and everything's going to move just a little bit. And that's something that we definitely don't want. So this would be easy to see that we could go back, add some more supports, make sure that that part doesn't move. And maybe those supports are unnecessary and we don't need them there anyway and we can just eliminate them. we can look at that too. So as you're looking at this, the cost of build failure, it's a tall part, pretty intensive to design and prepare for printing. There's a lot of cost tied up, and there's a lot of impact if this build fails. There's a lot of logistics. You have probably other builds queued up for that machine, and it really pushes your entire manufacturing back. And just that satellite bracket again, this is an excellent example of a very complex part. And it might be compliant enough that, some of the deformations can be, I guess, compensated for with some post-machining. And that's definitely built into this design. But really trying to understand how that part's going to come out and how to fixture it, what to locate off of, what you're going to get out of the printer, and it's going to be really important because you're going to do. I think these were titanium, so they're going to go to hip. They're going to have a lot of cost tied up in some of the post-printing operations before you can even decide if it's a good part. So if you can really get a feel for how well this part's going to turn out before you even hit the print button, you can really reduce your cycle time and really speed up your development, get parts out to market a lot faster. Just a quick summary, ways we can save time and money, because that's, not necessarily what it all comes down to, but definitely a very, very important factor. It's really important that 3DXpert is one software, one environment that you can do your entire workflow in. You can jump back anywhere you need to. You can make quick changes. You don't have to spend time jumping through different files. Files don't get lost. You're not spending time doing the same thing over and over as far as supports that worked and then just making changes to the ones that didn't. You can just jump back and just work on the ones that didn't work. You can really save money making quality builds on your machine, sellable product, instead of spending time doing a ton of iterations, a ton of development work. You can use that machine to make money, and ultimately that's what they're all there for. You can really reduce risk of build failures that, maybe they affect your machine, but they certainly, if they don't do that, they affect your logistics, your planning. There's always rework that has to be done when a build fails. And you can really try out novel ideas in a pretty risk-free environment. Say you want to try a unique orientation, maybe you want to try to see what would happen if you did a part up on its end, really minimal support, but it's tall and it would take 3 days to build. You can simulate it and see if it's even worth trying a build or doing more development on. So that wraps it up for me. We're going to open the floor up for some questions. I'll hand it back off to Dan.
Rocky, thanks. Like we said at the beginning of the webinar, if you have any questions, let's add them to the question and answer panel. I do have a few that I can start you off with, Rocky.
Okay, go ahead.
Oh, yeah, so there's obviously a lot of value in doing these build simulations, and I think one thing that was audience was wondering about was just the time to do a simulation. Specifically, there's a hardware question here. What computing power does it need? And can we do that calculation of the simulation offline or only on the computer that we're sitting at?
Okay, so I'll take that in chunks. First, the amount of time. Those ones that I ran were on a pretty typical workstation for the frame, and they took maybe just a few minutes to complete. Those are pretty small. They had probably 50,000 elements. But larger ones can definitely take a few hours, maybe overnight. Something that fills up the entire build volume on a 320, which we know is quite large, those can probably be an overnight simulation, depending on what your element size and layer height is. And then talking about calculation power, the meshing is done on a CPU. The simulation is done on a GPU, so you'll definitely want a machine with a pretty good balance. But I run these on my laptop. I could run most of them on my laptop, and as long as you have enough RAM, it should finish. But to that end, you can offload them onto just a calculation machine. So in the 3DXpert world, we call that the super box. And that's just a standalone computer. It doesn't have 3DXpert loaded, but it will do all of the offline calculations for build slicing. That's what it's been used for in the past. But now with build simulation, it will also do all of the calculations for the build simulation as well. So you can definitely simulate offline and not really tie up your workstation resources.
Great. I think the next question comes from where we were seeing you try different iterations of the part, and that is if the system will help you with ideas on how to reorient those parts, or were you just coming up with those on your own?
So I came up with those as basically good examples and talking points, but it's definitely exactly what I would do if I was developing a part. The suggestions for orientation aren't necessarily tied to the build simulation at this point, but 3DXpert does have a wealth of tools to help you analyze your orientation. So you can do minimum supported area, Z height, a lot of things like that. But it will definitely take some manual, I guess, intervention to decide, what the best orientation might be. Long cylindrical parts, we typically want to build axially in the Z direction, but that's just so we have a constant cross section. But it really might increase your build time. So it's all trade-offs, and that's something where, maybe the understanding from the build simulation will help you make more intelligent decisions on what you're giving and what you're taking.
Okay. I think the next question goes right to your experience with this product and the time you spent with it, because it is, without simulation, how many builds can you expect to do before you get a given print correct?
It's really part dependent. I'm pretty good at it at this point. It's taken me a little while to do, but I kind of have a 80-20 rule where I'll get a part to where I think it probably has an 80% chance of finishing. I kind of want to leave some chance for some failure and really validate my assumptions that that part or specific feature is going to be a problem. So if you do that intelligently, maybe 2 to 5 for a typical part, you might have a good part at the end. If you're doing simulations of those, you can really cut that time down. And maybe you can simulate some of those features, or maybe you don't even need to build some of those builds that I might do historically, just to try to understand the part and how it's behaving as it's being printed.
Okay. I think this is probably the last question on orientation, but it came in during the examples with the cube, and it should be asked, why wouldn't we build this part by laying it down on its side? Or maybe we were just looking at different examples.
Yeah, so that would definitely be the way that you would orient it for least deformation. But you probably necessitate a wire EDM to have that part removed from the plate. If the part's, I guess, valuable enough to warrant that kind of post-processing time, you certainly could. But I think you could see if we had it up on the edge and basically had it support-free, where you could just knock it off the plate, you know, you can remove a lot of that post-processing time, and you wouldn't have to necessarily stress relieve it like you would if you built it down on the plate. You'd have a lot of residual stresses tied up in the plate. I guess that's the long answer, but the short answer is I just wanted convenient examples that were pretty representative.
Okay. Actually, the questions are really rolling in here, Rocky, so I'm just going to get to the next one. There's a few about material. What material did your analysis run with, and is it possible to perform the analysis for composite materials or perhaps some polymers? So I know we were talking about metal here, but let's answer that one.
So I ran mine with Ti 6.4 grade 23, and that's pretty typical of a lot of the, you know, healthcare stuff. Low oxygen, pretty stiff material as far as titanium goes. I'm not sure about polymers and composites specifically. I know that the supports, if you do like a hat support like I did, they were homogenizing those based on density. So even though it looked like a, you know, kind of solid volume, it was basically had the properties of, you know, the hat support. So it's definitely might be possible. I'm not, you can certainly add your own material properties, you know, Young's modulus and things like that, but I can't necessarily speak to the accuracy of this simulation with those types of materials.
Okay. Little question on the whole process comes in. Will 3DXpert cover all the workflow steps needed between the CAD model and printing on an EOS M290 machine without having to use Materialize or another product?
So I'm not specifically sure about that EOS machine. I know that at a minimum, not just EOS specific, you can export CLI and slice files and put them into whatever your particular brand machine's hatching software is to actually draw the weld paths. But I'm pretty sure that there are definitely some machines in the library that you can export directly to. But that might be one that you might want to contact us directly about your specific machine.
Yeah, I agree. I think it would do any of the work up to the point of the actual slicing and printing to the format of that machine.
Yeah, certainly.
Yeah. Does the 3DXpert, can it be used with other technologies other than direct metal printing and other materials? I guess that's a little bit like our question a minute ago.
So you could probably use it to some capacity for other materials, and you could still get a slice file that you could drop into another hatcher, but it's definitely focused on direct metal printing. You know, that's its main focus, and a lot of the weld strategies and things of that nature are kind of focused towards different metals machines.
Yeah. That actually takes us to another one here, speaking of the strategies. So how does the software take into account the different laser scanning or hatching strategies?
So it's kind of a loaded question because that's one of the main strengths of 3DXpert. We do what we call, it's basically different regions is how you define what weld strategies are which. So I wish I had an example I could pull up, but you can add multiple different CAD models or volumes into that same part, right? So we could bring another model in, or I could use some of those design tools and make a volume that overlaps a portion of our part. And I can set that to what's called a virtual volume, and that will just override whatever scan strategy we applied to the bulk part. So as the computer is doing the calculation, it's going to first identify all of those different regions and decide what region takes precedence, and then it's going to go back and it's going to actually create all of those weld paths, and those weld paths will be merged together intelligently between the two build styles. So you could have, you know, I routinely do, you know, 4 or 5 different weld styles in a single part sometimes. And, you know, whether that's 30 micron layers or 60 micron layers, and that's all going to be accounted for during the slicing in one step.
Question here, getting back to the simulation. Does the software calculate optimum part constraints based on the part stress and thermals? Maybe it's about, you know, helping you with the supports based on that?
Yeah, so it's not going to give you direct feedback saying, hey, you should put a support here, you should change this. You know, it's very powerful in the simulation, but it still takes a trained eye and someone that understands, you know, the micro and macro level of what's actually happening in the machine, sometimes to draw some of those conclusions. It's just like the auto orientation tool. You know, you can give it some criteria, but at the end of the day, a lot of times we just have unique reasons why we want to print this part in this orientation. And I think it's going to be similar there.
Okay. Yeah, there was a question here about optimized orientation too, Rocky, and I think that, you know, we've covered that it kind of depends on different factors. Can you simulate the whole build tray with different parts at the same time?
You know, I haven't tried it with different discrete parts, what the typical workflow would be, but I don't see why you couldn't have the same parts on the build tray kind of merged together and do them as one simulation. I'm not necessarily sure it would be, I definitely don't think I would call it a best practice unless those parts are really integrally connected. You know, maybe they're wrapping around each other for some reason, but I would still kind of consider that one part. So maybe, but I probably wouldn't recommend it just from a practical computation standpoint.
And how do we determine what stress results are good? Is it only from visualization, or is it from your experience with the product?
So I think you're talking about plasticity here, where we're seeing some of the damage. So it's going to be somewhat unique to your process. So like I said, we do the physical calibration to your machine and your powder. You know, maybe even atmospheric environmental effects have some effect on your powder flow and weldability. So those would be captured in that physical calibration. But sorry, I kind of lost my train of thought there. What was the original question again?
I think it was really about just interpreting the results of the build simulation.
Oh, yeah.
You get the scale, stresses, and yeah.
The plasticity. So in this one, the plasticity range of 0.01 to 0.02 was where we started to see some failures. But that really has to do with your physical setup of your machine, because your machine is going to absorb some of those, like we saw in that last sample that we did, where you know, there's definitely some damage being done to the part, but your process might be able to accommodate it. So it's kind of going to come down to, you know there's damage, but how much can your process accommodate that damage?
Okay. I can see by the clock that we're really getting towards an hour webinar here. We have a few questions that we're probably going to have to answer offline. For example, the questions about support creation and infill structure. These get back to some of the other tools in 3DXpert, not necessarily the simulation. That would be a topic for a different webinar. So let's end with one here. Are there any limits to the build volume that can be simulated, or any limits on file size?
So build volume, it's going to be limited to the build volume of your machine. So it's not necessarily the volume that is going to be computationally intensive, it's the number of elements. So it's definitely possible to have a very small part and have a ridiculously small element size and just get a huge number of elements that you probably wouldn't be able to run the whole simulation. And that's just going to be tied to your physical machine, your amount of RAM. I'm not aware of any specific software limitations on file size or what can be accounted for in the simulation. The only thing I've seen is physical machine limitations.
Okay. You know, there's so many good questions here, Rocky. How about this one? Will 3DXpert help me with the post-processing operations as well?
Yeah, it definitely can. So there is an NC, CNC, I guess, numerical programming plugin. It's not even a plugin, it's an integral part of 3DXpert. And you can, if you do machine offsets through the machine offset tool in the build environment, those will automatically be flagged as needing to come off when you dump it into the CNC code environment. So you can definitely get a leg up on a lot of your post-processing. You can use some of the heat treat compensated models to see kind of what you can expect from relaxation for the heat treatment post-process, but certainly machining capabilities there as well.
Okay. We've got a few questions here that are general in nature about the materials supported, about the different printers supported, and I think we can get to those after. So let's call this the last one. Is it possible to simulate a situation where we start with a non-additive metal part and print on top of it? Maybe
That's
not.
a good question. I'm trying to think of a way to do that. I'm not sure if I can offhand, but maybe that's something that we can revisit offline.
Okay. Yeah, it might require a different type of printing technique if the part already exists. Thank you all for attending. Rocky, thanks for your help with this and the questions. Like I say, the webinar has been recorded, and if you're still with us, you'll receive an email with a link to that recording once we've processed it. Those of you whose questions we didn't get to, look for an answer offline. Rocky, anything else?
No, I appreciate everybody sticking with me today, and I think we had a good session.
Okay, thank you, and thank you all for attending.